Hello, my little minions. I video so we don't get too far. We all really worried behind while I was gone. So I saw a great little video to kind of touch up on a few things. It's isn't going to be like a full lesson, but I guess it's better than nothing for me anyway. Quick review. This is what we did last Friday, where I would give you a polynomial, and I wanted you to find all of the possible or all of the zeros. This one won't factor. So what we did here, if you don't remember, is we did factors of the first number over factors of the last. I'm sorry, it was the other way. Factors of the last number over factors of the first number. So factors of 3, the numbers that multiply to give you 3 are 1 and 3, and the factors of 28, numbers that multiply to give you 28. This is real jumpy. Oh yeah, now it's better. All right. Factors of 28 are 1, 2 goes into 28, 4 goes into 28, 5, 6, 7, 7 goes into 28, 14 goes into 28, and 28 goes into 28. So I'd start by listing possibilities. All the possible roots, possibilities are in factors of 28 over factors of 3. So that will be 1 over 1 and 1 over 3. 2 over 1 and 2 over 3. 4 over 1 and 4 over 3. 7 over 1, that's just 7, I think. I don't have my calculator handy, but I think 7 over 1 is 7. And 7 over 3, 14 over 1, and 14 over 3. Ah, geez, this is a lot. 28 over 1 and 28 over 3. And then you also have the negatives of all of those. So I'm going to kind of cheat just to make this video a little bit shorter. And really, y'all can do this if you want to, but you have the positive and the negative of each of those that you would have to test. And I showed you a little trick on the calculators that y'all could use. I'm going to show you how my 89. But instead of doing synthetic with every one of these, we have 2, 3, 7, 8, 9, 10, 11, 12. And their negatives gives you 24. So I'll show you a little trick you can do to speed up the process. So what I'm going to do, and here's my calculator. I have this on negative, so it'll show better. But let me use that. Punch that function in, and I actually forgot what it is. I'm going to have to go back to this screen so I can see it. 3x. Got that in right. Okay, so here I am on my calculator. I got my function in, and as soon as I'm going to plug in each. So I get negative 20. So that means positive. And I've just punched that in. So I'm ahead and cross out 1, because I know that's not going to be, well, that's not crossing anything out. Here we go. So that didn't work. So then I'll go back and I'm going to try 1. Just punch that in. Out 1/3, and this is starting to make me angry because I want an answer and I want it now. So now I'm going to try 2. Should have done this before I put it up here. So I'm going to pause the recording so I find the right answers. and I punched in, and the only work, let's put my calculator back. Plugged in 7/3, I got 0. You can see it right up there. So that means 7/3 is the root that works, and that's the only one, which is kind of frustrating. None of them worked, none of the others negatives worked. So x equals 7/3 was the only factor that worked. So that's the real 0. I should have said find all real zeros. That's the only rational 0 that works. To find any others, what I'm going to do is 7/3, and this is going to be kind of painful because it is a fraction. So I'm actually going to do synthetic division with 7/3 into my original polynomial. So I have 3x cubed, negative 7x squared, 12x, and negative 28. And even though it looks painful, it usually cleans up really nice. If I bring down my 3, 7/3 times 3, those 3's actually cancel and you're left with 7. Negative 7 plus 7 is 0, and this is getting kind of sexy. 7/3 times 0, 12 plus 0 is 12. And then 7/3 times 12, I'm actually going to come over here and do this. 7/3 times 12, 3 goes into 12 4 times, so those cancel, leaving me with a 28. And 28 is exactly what I wanted because I need a remainder of 0. And I'm left with 3x squared plus 12. That actually factors to 3x squared plus 4. And then that means this whole polynomial, since this is one of my roots, it will factor to 3x squared plus 4. And if 7/3 was one of my roots, that means 3x minus 7 was the factor. That's a lot tougher than I thought it was going to be. So if that didn't quite click with you, just hang on to it for a minute, and we'll talk about for a couple of days, and we'll talk about it when I get back. So 7/3 is the only one that really works, and this kind of ended up being ugly, but you list your possibles, factors of 28 over factors of 3, then plug them in one at a time. And in this case, 7/3 was the only one that worked. Then you could do synthetic to figure out what the rest of the function is. And that's what we did last Friday. I really wasn't hoping that would take 7 minutes, but hey, what the heck. Hey, now the new stuff, and I'm going to do this kind of quick because it is going to be on YouTube, and you do have the handout in front of you. If you need to go back and watch it again and pause it to catch up, you can do that. Go to the library, do it at home, something like that. Okay, complex numbers. Complex numbers. We've been doing real zeros. Now we're going to get into complex ones, and complex is just a fancy way of saying imaginary. So complex numbers are imaginary numbers. And they're always in the form a plus bi, and a few examples are 2i, 3 plus 5i, 2 minus 6i, any number plus a number times I. And don't forget, I is the square root of negative 1. And while we're talking about that, let's go through the iterations of I real quick. Iterations, that's not a word you use very often. If we know that I is the square root of negative 1, if I do I squared, that would be the square root of negative 1 squared. And if you square square root, you just get negative 1. So I squared is negative 1, and that's the most important one. We're going to do a few others, but I squared equals negative 1 is the one we're going to use more often than anything else. I cubed, I'm just going to go ahead and give this to you. It ends up being negative I. It's the same thing as negative I. And I to the 4th, we'll use that on occasion too. That ends up being positive 1. And after that, the process repeats. I to the 5th, it just goes in the loop. I to the 5th is the same as I to the 1st. I to the 6th is going to be the same as negative 1. I to the 7th is going to be the same as negative I. I to the 8th is going to be the same as positive 1. And then we'll repeat the same one. I, negative 1, negative I, 1. And it keeps repeating that process. So there's your things with I. That is kind of a repeat, so hopefully you've seen that before. And moving on to complex roots. Complex roots means you have an imaginary 0 or imaginary root. This function right here has an imaginary root, actually has 2 of them, because if you set that equal to 0 and you solve for x, you would subtract 9, x squared minus 9, or equals negative 9. You would take the square root, and what you can't forget is if the square root is your creation, I created that square root, x is equal to, that'll be plus or minus. That's what you have to do when you do a square root, and that'll be the square root of negative 9. I'm going to do this the long way first. That's negative 1 times 9, right? Yeah, that's right. I can pull out the 9 as a 3. So that's plus or minus 3 square root of negative 1, and the square root of negative 1 is I. So this is the plus or minus 3i, and those are my two complex roots. There are no real roots. This thing never actually hits the x-axis, so we have imaginary roots. We have complex roots. A quick blitz of doing square roots with i's. If you have like square root of negative 16, that's, hang on, that's neat. Hey, there we go. Square root of negative 16, square root of 16 is 4, and since it's negative, it's 4i. If I had something like the square root of negative 20, that's getting a little bit fuzzier, but the square root of 20, that would be 2 times the square root of 5 is the square root of 20, and the negative comes out as an I. So that's how we're going to do the square roots of negatives. And that's a complex root. It's a root. It is a 0, it is a root, it's just imaginary. We never actually hit the x-axis. Conjugate pairs theorem. Moving on down the page. By the way, I am following down this page that hopefully that has been handed out to you already. And I just did complex numbers. I just did complex zeros. Now we're about to do the conjugate pairs theorem. But what that says is you never have just one complex root. You have to have at least two. If you have one at all, you have a second one. They always occur in pairs, and they're always conjugates. And if you forget what a conjugate is, a quick note. I keep going to green. That's kind of hard to, I don't like green. Okay, the conjugate of x plus y is x minus y. All you do is change the sign in the middle. So if x equals 1 minus 3i is a root, then I automatically know, even if that's the only one that's given to us, you automatically know that x equals 1 plus 3i. That's the conjugate of 1 minus 3i. Then 1 plus 3i has to be another root. They always occur in pairs, and they're always conjugates. I'll make up another one. If x equals 2i is a root, then so is the conjugate of 2i. Now this one's a little bit weird because we don't have that number in front, but the conjugate of 2i is just negative 2i. So that's what conjugate pairs means. If you have one complex root, you have to have a second one, and they're going to be conjugates of each other. How to use that, like right here, it says find a polynomial when given the roots. And what I've done is I've given you 3 roots of a polynomial. Now the first 2 is stuff we've already done. If x equals 2 is a root, then that means x minus 2 is a factor. If x equals negative 3 is a root, that means x plus 3 is a factor. Now where it gets a little bit fuzzy is with this new stuff. If x equals 4i is a root, then I can automatically conclude I know that x equals negative 4i is also a root. They always occur in conjugates. So even though they only gave us 3, I know there's a fourth one, the conjugate, which is x minus 4i. And the way we always get the factors is it's always x minus whatever the root is. In this case, 4i. The other factor is going to be x minus negative 4i, which is plus 4i. And that's where we're going to start writing our polynomial. Now here's where it's going to get ugly. I like having imaginary numbers in my answers. We have to find a way to fix that. And I'm looking right here, looking at this stuff right here. I don't want those complex numbers in my answer. So what I'm going to do is anything that has a complex number, we're going to expand those things out. Now the x plus 2, x minus 2, x plus 3, these are okay. We're going to keep those. No complex numbers at all in that. So we're going to keep these as they are. You don't have to expand those. Keep has 2 these, I think. Keep these, we're going to have to expand. So expanding x minus 4i, we're just going to FOIL it. X times x is x squared. X times 4i is going to be 4ix. Negative 4i times x is negative 4ix. Negative 4 times positive 4 is negative 16, and I times I would give me an I squared. So I've expanded those 2 out, and we should get some sexiness here. 4ix minus 4ix cancels. Leave me with x squared minus 16i squared. Now you're probably worried because we still have an I. There's still an I in that, and I don't want imaginary answers. I don't want imaginary numbers in the answer. But if you remember, back here, we said that I squared is the square root of negative 1. So when I have 16i squared I know is actually the same thing as a negative 1. So this becomes x squared plus 16. The I squared is negative 1, so negative 16 times negative 1 is plus 16. And those things that we're going to keep, they just come on down for the rod. And my final answer is going to be x minus 2, x plus 3, and x squared minus 16. That's the polynomial with those roots that were originally given to you. If you have one complex root, you have to have the second one. Let's try another one. X equals 1/2 and x equals 1 plus 2i. Let's see an imaginary root. If I see any imaginary roots, I can automatically conclude there is a conjugate that goes with it. The conjugate of 1 minus 2i is, or I'm sorry, the 1 plus 2i is 1 minus 2i. So I actually have three roots, 1/2, 1 plus 2i, 1 minus 2i. So I'm going to start writing this one out. My function is going to be y equals, now if x equals 1/2, if that's my root, that comes from a factor of 2x minus 1. Now it's going to get really fuzzy. You're not going to like this. We always do x minus the factor. Now my factor is getting a little bit uglier. Right here, my factor is 1 plus 2i. So I need to do x minus, in parentheses, 1 plus 2i. Then I'm going to do the same thing with this one. That root is 1 minus 2i. I'm trying to keep this kind of color-coded. So my next factor is going to be x minus, and then in parentheses, 1 minus 2i. And then we're going to have to do the same thing we did on that last problem right here. If you have any imaginary roots or any imaginary parts of your answer, you have to expand it. So I'm going to have to expand all of this out, and it is going to be a little bit ugly, but it cleans up pretty quick. 2x minus 1 is okay. I'm going to keep it. It's just going to come along for the ride. Here I'm going to start working this out. I'm going to distribute my negatives. That'd be x minus 1 minus 2i times x. If I distribute this negative, that'd be minus 1 plus 2i. And now I'm going to expand these two things right here. We need to expand this. And you have to keep your work organized, but a lot of stuff will cancel. It's going to end up being kind of nice. X times x is x squared. X times negative 1 is negative x. X times 2i is 2xi. Negative 1 times x. Negative 1 times negative 1. Negative 1 times 2i is negative 2i. Negative 2i times x is negative 2xi. Negative 2i times negative 1 is plus 2i. Negative 2i times positive 2i is negative 4i squared. I forgot to write the squared. And don't forget, 2x minus 1 is just kind of hanging out here, doing its own little thing. Now we start canceling, and we should get a lot of cancelage. 2xi and negative 2xi cancel. Negative 2i and positive 2i cancel. Nothing combines with the x squared, so that's going to come down. Negative x, nothing combines with that. That comes down. I didn't see, there's a negative x right here, so we actually have two negative x's. I'm sorry. Negative x minus x is negative 2x. And then I have a plus 1 right here, and a minus 4i squared right here. Oh, but I see that 4i squared again. What is I squared? What is I squared? Anybody? Anybody? Answer, answer, answer. What? That's right. Good job. I squared is negative 1. So when I see negative 4i squared, that's really saying negative 4 times negative 1, which is actually a positive 4. So negative 4i squared, that actually turns into a plus 4. And then I can combine my 1 and my 4. So x squared minus 2x, 1 plus 4 is 5. And don't forget, 2x minus 1, don't forget it, it has feelings, you don't want to leave it behind. There is the final answer. Heavy, heavy on the algebra, you have to be really careful with your work. But you need to expand anything with a complex root, expand it until those i's go away. Something a little bit easier. What we just did, I believe, is the hairiest and most cumbersome part of this section, and that's the tough part. 19 minutes. We got to finish up this soon. That's probably the toughest part. So something that's a little bit easier. Prove that the proposed x value is a root, or are roots. Well, there's really whatever. So I need to prove that x equals 2 is a root for this function. And the easiest way to do that, and is what we did Friday, is just do synthetic division. If x equals 2 is a root, then that means 2 will divide evenly, synthetically, into my function. So I have 1x to the fourth, negative 1x cubed, 7x squared, negative 9x, and a negative 18. And I'll do synthetic division. And if it is a root, I should get a remainder of 0. So bring down the 1. 2 times 1 is 2. Negative 1 plus 2 is 1. 2 times 1 is 2. 7 plus 2 is 9. 2 times 9 is 18. Negative 9 plus 18 is 9. 2 times 9 is 18. And when you add those, we get a remainder of 0. So we just proved that x equals 2 is a root. And we can draw Triangle Man and be happy. You can watch Triangle Man dance. Doing, 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 dancing around, blah, blah. He likes to do flips too. Watch this. Whoa! All right. And then he likes to bounce off the walls. Woo! Okay. So anyway, there's Triangle Man. He's happy because we just proved that 2 was a root. That one's nice because 2 is a real number. You can wrap your head around that. I know what 2 is. I have $2, and that's great. So it gets a little bit fuzzier when you have a complex root, but the process doesn't change. Same function, but now I'm saying 3i is a root. Well, here, don't let it scare you, but we're going to do 3i synthetically into all of this. Now, I'll put a lot of room. I don't know how much room I'm going to need, but I'm going to space it out just in case. I have 1x to the fourth, negative 1x cubed, 7x squared, negative 9x, negative 18. Now I'm going to do synthetic division, and work with me here, but it's going to work out nice. Bring down the 1. 3i times 1 is 3i. Negative 1 plus 3i is 3i minus 1. You can't combine those. I'm going to put that in parentheses just so I can remember what it's grouped with. Now I'm going to distribute my 3i. So 3i times 3i minus 1. 3i times 3i minus 1. 3i times 3i is 9i squared. 3i times negative 1 is negative 3i. But remember, I squared is the same as negative 1. So this is the same as negative 9 minus 3i. So I'll put that here. Negative 9 minus 3i. Combine 7 minus 9 is negative 2 minus 3i. And I'll multiply again. So let's get rid of this. And I'm going to multiply again. 3i times negative 2 minus 3i. Distribute negative 6i. Negative 3 times negative 9i squared. And again, don't forget I squared is negative 1, so this is the same thing as negative 6i plus 9. So negative 6i plus 9. Ooh, that's nice because negative 9 plus 9, that cancels. That just leaves negative 6i. And now when I multiply, 3i times negative 6i will be negative 18i squared. I squared is negative 1, so this is really a positive 18. Negative 18 plus 18 is 0. We get a remainder of 0, and we get to sing and dance because we just proved that 3i is a factor of that polynomial. Questions, comments, concerns? Great. That's just wonderful. Now, the place where it gets really fuzzy is when you have a like 3 minus 2i as a root. This is going to take a little bit of space, but I'm going to show you a little trick on the calculators that can help you. And 84s and 89s both do this. But we're going to do the exact same thing, 3 minus 2i, synthetically into that big function. I'm going to leave a little bit of space because I think it's going to need some space. So 1, negative 9, 21x squared, 21x, negative 130. Now, negative 130 scares me, but I'm hoping this will clean up very nicely. So first thing we're going to do is bring down the 1. Anything times 1 is just that anything, so 3 minus 2i. Let's combine. Negative 9 plus 3 is negative 6 minus 2i. And now here's where it gets fuzzy because I need to do 3 minus 2i times negative 6 minus 2i. Now you can multiply that out by hand, and I expect you to be able to do that when I get back. Do this on the calculator. So I'm going to go back to my calculator. Above the catalog right here under the apps, you'll see a little script. Same. I forgot what it was. 3 minus 2i times negative 6 minus 2i. I'm going to punch that in. Go back to my calculator, show you what I just punched in. So there you see, I missed a button. It's not negative 62i, it's negative 6 minus 2i. And when I hit enter, it tells you negative 2 plus 6i. So that's what they multiply to, negative 22 plus 6i. And so I'm going to add 21 minus 22 is negative 1. And I'm going to multiply again. It's 3 minus 2i times negative 1 plus 6. Go back to my calculator. Plus 20i. So 9 plus 20i. We'll add those. 21 plus 9 is 30 plus 20i. Now I need to multiply again. 3 minus 2i times 30 plus 20i. Go back to my calculator. So 30 plus 20. What it was. This is so frustrating. 30 plus. I hit enter, and we get 130. It cleans up to simply 130. So I get 130, and here. 130, negative 130 plus 130 is 0. I got a remainder of 0, and a problem like that deserves a big hefty triangle, man. So let's get a nice triangle. Ooh, I know what we can do. Let's do a colorful triangle, man. Check this out. So we'll do a colorful triangle, man. There's his eyes, here's his mouth, and Triangle Man is happy because we just proved that 3 minus 2i is a factor of that big ugly thing. So here's Triangle Man dancing around. Booty, 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 poopity, poopity, poop, ba, 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 ba. Who flip? Whee! All right. Good. And this is getting kind of long already. I didn't want to go over 20 minutes, and I'm already looking at 27. Yikes. So we'll come back to some of the other stuff later.